Okay, welcome everyone to the final FPGA seminar of the year. Today's seminar will be given by Miyadi Shah on the subject of, on the difficulty of pin-to-wire routing in FPGAs. All yours.
Thanks, John. So good morning, everyone. Today I will be talking about the difficulty of pin-to-wire routing in FPGAs. Before I get started, however, I think it would be interesting to note how this project got originated. My supervisor, Jonathan Rose, was reviewing a paper for the FPGA conference, and the paper involved using the internal multiplexers of the FPGA's routing fabric as logic multiplexers. So there were three other reviewers for this paper: Steve Trimberger from Xilinx, David Lewis from Altera, and Von Dutz from Altera, who was also working at Altera at the time. All three of them thrashed the paper on the basis that it required pin-to-wire routing to work. Jonathan, however, did not realize this at the point and liked the paper, but later, on reading the reviews of the other reviewers, he realized his mistake. However, his curiosity was aroused, and he felt that pin-to-wire routing could succeed under certain circumstances, probably with some low-cost modifications to the architecture with some good algorithms. And in order to discover that, he launched this project. That is kind of the origin of this project, but not the direct motivation behind this work. So FPGA routing architectures are large-scale interconnection networks. They are meant to provide quantity and flexibility of routing to provide connections for a large variety of application circuits, but to make connections from pin to pin. That is, from a logic block output pin to a logic block input pin. However, sometimes FPGA architects and tactile designers may get motivated, for reasons that I'll explain later, to use this interconnection network in a way that it was not intended. That is, to make connections from logic block output pins to specific target wire segments within the network, or from specific target wire segments within the network to logic block input pins. However, there may not be enough flexibility in the network to support these kind of connections, but we'll get to that later. First, let's look at the motivations behind pin-to-wire routing. The first motivation behind pin-to-wire routing comes from the need to perform routing by abutment. Routing by abutment involves having pre-placed and pre-routed logic blocks that connect together by abutment of specific wire segments in the interface. This is somewhat similar to what is commonly done for power grids using 8/6 standard cells. Let us understand this better using an illustration. Okay, for example, we have this function, f, and we wanted to implement it using routing by abutment. The one way we could go about doing this is to take a pre-placed and pre-routed adder from our library, connect to it a pre-placed and pre-routed divider from our library, and then simply place them together. On placing them together, the wire segment interface connects and our circuit is synthesized. For this to work, the different modules could be synthesized separately. When they are synthesized separately, then the nets that are crossing between the modules would require pin-to-wire connections. For example, if we had a net going from the adder module to the divider module, the adder module would have routed it from the logic block output pin to a specific wire segment in the interface. The divider module would have accordingly routed it from a specific wire segment to a logic block input pin. When the two modules are placed next to each other, the two halves of the net connect and the net completes. Clearly, the pin-to-wire connections are required, and they require efficient pin-to-wire routing to work nicely. As the illustration showed, the logic modules could be synthesized independently from each other, provided that we know which specific wire segments the connections are to be made of. This idea can also be extended to multiple modules connecting in the same wire manner, but using the same wire abutment pattern. From our previous illustration, we can also see that the need for intermodular routing was completely eliminated. The elimination of need for intermodular routing, along with the post-placement of the logic modules, could help us reduce a major portion of the compile time. Reducing compile time has become a motivation for modern FPGA architectures. First, because modern FPGAs are becoming larger in size, and consequently, larger and larger circuits are now synthesized onto those FPGAs. The processors running the CAD compile, however, have not kept pace, and so the compile times are increasing. Placement and routing form a large portion of this compile time, and hence, by trying to eliminate or even reduce them using techniques such as routing by abutment, can help us save on compile time, making FPGAs more attractive to users. Now, Our second motivation for pin-to-wire routing comes from partial runtime reconfiguration of FPGAs. In partial runtime reconfiguration, specific areas on the FPGA are designated to contain different modules at different points in time. Again, let's take a look at an illustration. This is our function from before, and this is a circuit that synthesizes that function. Let's say at some point during the runtime of the circuit, the function f changes so that now it requires a multiply operation instead. Well, partial reconfiguration will allow us to remove the divider module and replace it with a multiplier module. Just like routing by abutment, nets that were crossing between the modules would require pin-to-wire connections. These pin-to-wire connections would again require efficient pin-to-wire routing. Our third motivation for pin-to-wire routing comes from the use of circuit elements within the routing fabric. For one such example we can take is that of multiplexers. Multiplexers are very expensive to implement in soft logic, but there are plenty of multiplexers within the FPGA's routing fabric. So we could use those as logic multiplexers. Let's look at an example. Let's say if this was an input connection block multiplexer that we planned to use as a logic multiplexer. In order to use it as a logic multiplexer, we would have to make a couple of changes. First, we would have to change the static control of this multiplexer to dynamic control. And second, for each of the multiplexer's inputs, including the control inputs, we would have to drive them from specific logic block output pins. Or in other words, we would have to drive specific target wire segments in the interconnection network from logic block output pins. Again, we require pin-to-wire routing for this to work. So, although pin-to-wire routing has a lot of motivations, but the need for pin-to-wire routing conflicts with the basic purpose of the FPGA architecture, which is to provide a quantity and quality flexibility of routing to enable pin-to-pin connections. Pin-to-wire routing suffers from a lack of flexibility due to lack of interconnection stages in the network, and as a result there are much fewer ways to get in and out of a wire segment as opposed to a logic block. Clearly, we can expect pin-to-wire routing to be more difficult as pin-to-pin routing. But we also know that most FPGAs are somewhat over-architected in order to provide a quantity and flexibility of routing to support the routing demand for a broad class of application circuits with a varying demand for routability. So this leads us to believe that we can use some of this extra routability to help us mitigate the loss of routability that we would face when we encounter pin-to-wire routing. So our goal through this project is to first test if our hypothesis is true, and second, to measure the impact of pin-to-wire routing on the router and the routing architecture's performance in terms of wire length, critical path delay, and router effort. We measure router effort in terms of heat push and pop counts. These are terms that I'll explain later when I get to the results. First, let me take you over the top-level design flow of our experiments. We begin by taking a netlist in its glyph format, pack it using TVPack, and follow it by placement and routing using BPR5. The benchmarks we use are the biggest 20 MCNC benchmarks, and the architecture we use is a classical architecture with 4 4-input LUTs per cluster, an input connection block flexibility of 0.15, output connection block flexibility of 0.25. The wire segments used are all length 4 with a staggered distribution, a single driver approach, and a built-in switch block with a switch block flexibility of 3. Next, I'll begin by talking about some of the experiments that we performed and their corresponding results. The first experiment that we designed was meant to simulate the routing by abutment motivation that I talked about earlier. To simulate routing by abutment, our design methodology was then as follows. We began by taking each benchmark circuit and running packing, placement, and routing on it using BPR, and determining the minimum number of tracks required to route the circuit. Next, we ran the replacement and routing step, but now at 30% higher than minimum channel width. This extra channel width that we provided is sort of like a leeway that we gave to the circuits so that pin-to-wire routing is more easily performed. The routing that we received at this point is called base routing, and the measurements that we made on this base routing, including wire length, critical path delay, and router effort, were recorded as base measurements. At this point, after this point, we'll change the architecture a little bit and rerun our experiments, and that would be the second routing phase. But for the second routing phase, it's important that we introduce pin-to-wire connections in our netlist, because that is what we're trying to measure, pin-to-wire routing. To do so, we begin by taking the FPGA grid and drawing a hypothetical line down the center of the FPGA. This leads us to create two modules, a left module and a right module. These two modules can be thought of as two modules in a routing-by-abutment scenario. Such a division of the FPGA will now divide the nets in the netlist into two types of nets. First are the single-sided nets. These are nets whose terminals lie completely within one module. Second are the double-sided nets, or nets whose terminals lie in both modules. Now, in a routing-by-abutment scenario, we would expect that double-sided nets are the nets that cross between the modules, and those are the ones that will generate pin-to-wire connections. So, we replace the double-sided nets with pin-to-wire connections in the netlist. To do that, we do the following. We look at the base routing of the double-sided net, and from that base routing, the first wire segment at which the base routing intersects our hypothetical FPGA boundary, like here, we choose as a target wire segment. Using this target wire segment, we create pin-to-wire connections. Our first pin-to-wire connection includes the source, that is the original net source, and the target wire segment acting as a sink. Our second pin-to-wire connection includes the target wire segment acting as a source and the net's original sink. We replace the double-sided net with these pin-to-wire connections, which we also call 4 nets. A possible routing for such 4 nets would be like this. The issue becomes a little more complicated if the base routing crossed the hypothetical boundary twice or multiple times. In that case, then, we go back to our motivation and we observe that in a routing-by-abutment scenario, we would rarely have a net that would be allowed to cross the interface twice. So to emulate that, we restrict our crossings for double-sided nets to be single crossings, even in our second routing phase. We do so by selecting only one of the target wire segments. In this case, we select the first target wire segment. This target wire segment is then used to fork pin-to-wire connections. Our first pin-to-wire connection would then involve the original net source, the sinks that lie in the same module as the net source, and the target wire segment acting as a sink. The second pin-to-wire connection involves the target wire segment acting as a source, and the remaining net sinks. Again, a possible routing of those 4 nets could be as follows. Notice how the second half changed its routing, second 4 net changed its routing to now accommodate only one crossing point. After all the double-sided nets are replaced with their pin-to-wire connections as shown, we rerun the routing phase. Before we get to the results, however, it is important to note that the pin-to-wire selection of the target wire segments turned out to be quite important, because a poor selection could result in a deterministically unroutable circuit. That situation could occur in 3 ways. First, we select several target wire segments such that they are in close proximity to each other and they block each other from routing success. Second, we select target wire segments such that they completely block an input or an output pin. Or third, we select them such that they have insufficient exit points. Again, let's take a look at an example. This is an input connection block multiplexer which connects to only 3 wire segments in a channel segment. If we were to select all 3 of these as target wire segments for, let's say, net X, Y, and Z, then for a net A that was actually supposed to use this logic block input pin, it has no way of accessing the input pin anymore without clashing with one of the nets X, Y, or Z. Clearly, routing would be impossible in this scenario, and we would get a deterministically unroutable circuit. So target wire selection is very important. And we also note here that because without this process we would end up with a large number of unroutes, this clearly talks about the difficulty of pin-to-wire routing in FPGAs. Moving on to the results, our results are a comparison between our base routing phase, which was our first routing, and our second routing phase, which we now refer to as split routing. Since our split routing is somewhat based on our base routing phase, the target wire segments were selected from the base routing, we don't expect the results to be much different. The results are somewhat different, however. The wire length reduces by 4%. The critical path delay increases by 5%. The router effort, which is described in terms of heap push and pop count, increases by 11 and 99% respectively, and we have two unroutes. Now the heap in VPR is a priority ordered queue of the wire segments that are meant to be pursued. So the push count measures the number of nodes that are placed on the heap to be explored or as potential candidates for exploration, whereas the pop count measures the number of nodes that are actually explored to arrive at the solution. We use them instead of runtime because these are processor independent. Next, we can see that the wire length is reduced by 4%. Now there are two reasons for this. First, the decrease in wire length could be because that we started off with a known good solution, and that gave VPR extra time to arrive at a better solution. We did select the original target wire segments from the base routing of the nets. A second possibility that results in the reduction of wire length could be that we restricted the double-sided nets to have only a single crossing point in our second routing phase. This means that we could have sacrificed critical path delay for wire length. Our second hypothesis can be borne out by the increase in the critical path delay. Looking at the results, however, one can be led to conclude that pin-to-wire routing can be achieved with a relatively low price to be paid. But that may not really be the case because we started off with a known good solution. That fact could be misleading. So we designed a second experiment in which we make sure that we do not use a known good solution. We do this by choosing a target wire segment that is explicitly different from one that was chosen during the base routing, and we do that by selecting a target wire segment which lies in approximately the same row or column location as the original target wire segment, but is different from the original target wire segment. Again, let's look at a figure. If this was a double-sided net, then in experiment 1, this would have been our crossing point and our target wire segment. In experiment 2, we would change this so that we could choose a different target wire segment. Let's say we would pick this wire segment as our target wire segment. Again, we would follow the entire procedure, create 4 nets, replace the original double-sided net with these 4 nets, and rerun the experiment. The results now show that our wire length increases by 6%, critical path delay increases by 15%, push count by 86%, and pop count by 327%. We also have one unroute. The router is clearly working much harder to achieve those results. But if the target wire segments were to be selected carefully, pin-to-wire routing is possible with some price to be paid in terms of critical path delay, wire length, and router effort. All the experiments that we designed so far, however, were an approximation to our routing by abutment motivation that I presented before. But there were other motivations such as the need to use the circuit elements within the routing fabric. So in those scenarios, it would be important to know how much pin-to-wire routing could we introduce in a netlist before we significantly impact its area, speed, and routability. To do so, we would like to vary the amount of pin-to-wire routing that we are introducing in a netlist. And we vary that by varying the amount of nets that are being split. I'll go over the design methodology for this experiment. The base measurements were acquired as before, just like for experiments 1 and 2. But the second routing phase was modified. In the second routing phase now, we select a fraction of nets F from the netlist. For each such selected net, we look at the base routing and we pick a target wire segment from the base routing that lies in the center of the net's bounding box. Using this target wire segment, we again create our pin-to-wire connections. The first pin-to-wire connection consists of the original net source, the sinks that lie on the same side of the wire segment as the source, and the target wire segment acting as a sink. The second pin-to-wire connection consists of the target wire segment acting as a source and the remaining net sinks. Once all the selected nets have been replaced with their pin-to-wire connections, we again route the netlist. Results show that when we increase the fraction of nets that are being split from 20% to 100%, which is we increase the amount of pin-to-wire routing in a netlist, the while length reduces from 1% to 7%, whereas the critical path delay increases from 4% to 16%. The router effort, accordingly, also increases as the amount of pin-to-wire routing introduced in a netlist is increased. In the worst case, the heap push count doubles, whereas the pop count quintuples. From the results, we can see that it is clearly there is a price to be paid to perform pin-to-wire routing, and as the amount of pin-to-wire routing in a netlist increases, this price increases. But the price is not always prohibitive, and pin-to-wire routing can be performed under certain scenarios. To conclude then, we measured the difficulty of a pin-to-wire routing faced by a router and a specific routing architecture. We showed that the wire length increases significantly, critical path delay increases significantly, and there is also an increase in router effort. There is an occasional loss of routability as well. Our current work focuses on measuring the impact of routing architectures on pin-to-wire routing. With that, I'd like to conclude and thank you for listening. I welcome any questions that you may have.
Might as well start off with one of the people who trashed that previous paper. So in your early comments, you said there's extra routability in FPGAs, and in your methodology, you do W plus 30%, but that's not really realistic compared to commercial products. There isn't extra routability. We barely route the hard-to-route design. So you're basically getting the extra, using that extra 30% of slop to compensate for the increased difficulty of routing. So what I think would be more interesting is if you actually took your architecture at the minimum W that routed, then you applied this and you saw, well, how much extra routing do I need to make the design continue to route? Right? Because we don't know how much of that extra 30% slot, which doesn't exist in a real FPGA, is covering that. Some other issues is that the academic architectures have a lot, I think they have a lot higher degree of connectivity than we have in something like a Strat. It's like you have an FC of 0.1 and you have an FC of more like 0.02. And there's also the physical issues of the patterns that VPR generates are connected to a much wider fraction of the channel than you can actually physically build. And this isn't specific to your work. It applies to everything in general, but in the case of your work, it may be more of a constraint because I've got the LE in the top of the lab. VPR will pretend you can talk to 10% of the wires in the channel, but the reality is those 10% are crunched towards the top part of the channel. So that was a lot of comments for one question.
I agree with your first point. So we are going to measure how the performance changes when we vary the minimum channel width when we vary the channel width from 0% to around 50%. And the second, but I don't have to
interrupt though, there's a question about that.
Yeah.
You said the hardest to route circuits are at
They're at WMN, and they're getting Fmax degradation because they're barely routable, right? And
but that's one of a set of amongst the distribution of all the circuits that are routed. So
the easy to route circuits, yeah, they have 30% slop and they could use this, right? But we can't go to our customers and say, okay, you're a hard to route circuit, you can't use this methodology. And you guys over here that you're easy to route, you can lock down these pins and do routing by abutment.
Or you could say, if you want to do this, then you have to do something that makes the circuit easier to route. Then you have to give up some space or something
yeah,
that's spread it out.
I don't think anyone's going to want to pay the extra 20% part cost for that either, right?
Depends on what they want what this gives you, right? So,
right.
But you're focusing on the tail end of the distribution, and the extra routability that's put in is always to service those folks. Yeah,
but so they are right at the edge of routability, and if we use this, we're going to need to add more routability or have more of their density. So with that's possible, but you need to actually measure that cost, not just buried in this W plus 30%. And you're extracting a little bit of the Fmax cost, which is one cost. The wire length is a very indirect thing, because you really need to measure how much more routability you need to add to use this methodology.
Yeah, that's what we're going to do. Yeah. Sorry, I interrupted you. You were going to answer his second comment,
which was the impact of FCN
and also physical constraints, like one LE can only talk, not do a bunch of wires scattered across the channel, but one LE output can drive like wires into the top quarter of the channel, right? And that could increase the difficulty of using this approach by a bunch, I think. And
Yep.
it's something it's not modeled in VBR, it's not even modeled in the, tool we use internally in Altera, right? But it's something that could really bite you in reality.
So definitely, studying the effects of architecture on pin-to-wire routing is our second part. So we are working on it currently, and we are going to investigate some topological effects, such as like which wire segments would connect to the input pins or output pins.
There is something about the quantity going on. These are the small MCNC circuits, so the channel widths are really small,
Yeah.
and so some of these effects are completely invisible to these experiments. So if we had bigger circuits and larger clusters, we could, or FC of 0.25.
Yeah.
Like the fractional FC is a
wider channel.
yeah, it should go around. It really should be
Yeah.
a constant FC, right?
Yeah.
Fractional. So there's some of that is hidden away in those facts.
There was a lot of work in custom ASICs about Steiner tree routing, where you're choosing, for example, you look at where those target pins are, and then you choose an intermediate point route from the driver up to the intermediate points, or points, right, point or points. Then you hit the targets from there, right, to try to minimize overall wire length. Seems to bear some semblance to what you could do with this, right? And people, I think, there's been a lot of work on that and trying to, for example, do that to minimize total capacitance and power. So it seems like that.
You're talking about the selection of the target wire segment, like where
Yeah,
we
that
select-
intermediate wire segment, whereas that Steiner, all that Steiner routing stuff in ASICs, it didn't really apply to FPGAs because of this problem. You couldn't choose intermediate good points to route out to then hit the targets. But if it turns out to be relatively low cost, like you might want to look into a little bit of that literature on how to choose the intermediate points, to minimize total overall wire usage.
Definitely.
Because you're kind of choosing intermediate points here based on routing each load independently, right? At least in your first experiment right there. Which, if you could choose a good intermediate point independent of how they were routed in the first pass, you might do something different. So, and maybe, people in custom ASICs, I know there's a whole body of literature on that. You could at least take a look at it.
It's actually an interesting point, because one of the strange side effects in the first experiment was instead of crossing the boundary twice, we cross it once
Yeah,
and pick one of the
right.
bad ones. And if we picked something else that was better,
That's what I mean,
we
yeah.
wouldn't take the same hit in critical path delay,
Yeah.
and still keep the win in, well, it would be better for critical path delay.
Yeah, and I think in ASIC land, there's been a lot of work on how to choose a good branch points, those kind of intermediate points.
I suspect in the abutment routing may not be as applicable because you don't have knowledge of both sides when you're doing the routing.
Right.
So essentially it is doing it one at a time,
Yeah.
and crossing things is somewhat random or arbitrary.
Yeah, I guess the abutment is one application of this. Another application would be just to produce good routes for signals with the distribution of loads, right? By finding good intermediate branch points to route out to.
If you could convince yourself that it wasn't going to kill you somehow else.
Well, yeah,
Which is
that's
part of the
that's
point.
Dave's question too.
Oh, that's interesting.
When you were doing the first part where you split, I'm assuming you split the chip down the middle and then fix all of the crossing nets. Did the placer get modified to kind of partition out the placement to minimize the number of nets crossing?
No, the placement was kept the same from the base placement that we had. Only the routing phase was we learned.
So I'd imagine that the standard placer would kind of cluster things down the middle, and if you slice it down the middle, you would actually get much more than a realistic number of nets that are crossing the boundary.
Can you repeat that?
So if you use abutment routing, usually you would have, say, two clusters of circuits where the connections would be kind of clustered within each, within each part, and then there would be a few crossing nets. I'm just asking whether your placement was modified to kind of approximate that, rather than if you just do a flat placement, chances are it'll be this big blob of circuit, and most of the nets will be crossing through the middle. rather than splitting it out and having fewer crossings.
So, no, we haven't studied the effects of placement, like changing the placement on the pin-to-wire connections, but we do expect that if we do a new placement, then the results might get better because of that.
We actually thought a lot about that, about redoing the placement. Actually, that's not what you're talking about. You're talking about doing the placement knowing that you want to
There was
minimize
a-
crossing.
Yeah,
we didn't
design
think of that.
hierarchy, then the cut line
Yeah.
would be smaller than just flat placement.
Yeah. I guess it goes to how would you design the interface if you were doing routing-by-abutment? It's kind of that process speaks to, can you make that integration of the interface points better? We didn't think, we walked a little bit down that path, but decided we just wanted to measure, given